All right, everyone, we'll get started. Hello, I'm Kaslin Fields, and I'm a CNCF ambassador, and I am your track host today. We're introducing track hosts at this KubeCon. Hopefully you've seen us around. I'm going to introduce your talk real quick, and then at the end, I will be passing around the mic for Q&A. And I am here to remind you to please do your feedback forms at the end of the session. We really appreciate it, and your presenters can learn a lot from the feedback that you give. So we are ready today to hear about Ready to Serve, Speeding Up Startup Time of Istio-Powered Workloads from Michal, Etai, and Zvi. Take it away.
Thank you.
Okay. Thank you very much. Hello, everyone. My name is Michal, and I'm a manager at the IBM Research Lab in Haifa.
My name is Etai, and I work also at the Research Lab. We've been with the Istio since pretty much its inception, and we'll try to keep today's talk brief, short, to the point. I know everybody wants to go back home. It's been a long 3 days, so we'll try and keep it focused.
Yeah. Today, Etai and I are going to talk about startup time of Kubernetes pods, and more specifically, pods that are installed with Istio on them. After we will be clear on what does it mean, Istio inside this pod, we will continue and introduce you to a few techniques on how to speed up pods, which are Istio-enabled on them. So before we'll start, let's first define what we mean by startup time. So startup time is from the point that the user is requesting Kubernetes for a new pod, which is creating and sending a new request, till the time that the status of the pod is ready by the Kubernetes API. And why is it important? It is important because a lot of various components are waiting for this status to be ready, so they will be able to start and use this pod. For example, Istio is one of the examples, and we will see how it will work. Knative, a lot of time, is waiting also for the pod startup time, and Kubernetes, of course. And why do we care about startup time, and in which use cases is it really important? So we have a few examples here. The first one is, for example, serverless, and more specifically, scale to zero, scale from zero. In serverless, the pod is starting only after new requests are coming. And then it is very important the time that the pod is ready, because only after it is ready, the request can be served. More use cases are auto-scaling. In auto-scaling, when we have a load on the system and we would like to move requests to new pods, we need to wait to the pod to be ready. And last example is for recovery from failures, when it is also very important because all the requests are waiting, basically not getting any response till the pod is ready. So what's actually happening when pod is starting in a high-level view? So first of all, the user is sending a request to the API server to create a new pod. Then the API server authorizes and authenticates the request using some access control system. It is calling to the admission webhook to validate or mutate the pod. And we will see later how exactly Istio is coming inside it using another admission webhook that is coming in, and how we will see an example of how exactly it's influencing the startup time. etcd is it's a persistent source that Kubernetes is using to hold all the information about the object. And here, API server is saving all the object information inside etcd. We will see also after that in any point that we have new information about the object, it is being saved into etcd. The scheduler is listening to the API server, and at the point that it's seeing a new object that is being created, It is looking for a node and attaching it to this object, and saves the information into etcd. So all this so far that we've seen happening in the control plane. Still, we don't have any container and any pod that is running yet. Let's zoom out and see what is happening on the worker node.
So if we keep the control plane on the left, all of that happened on the control plane. Now we're going to shift our focus into the worker nodes. So there's an agent, and I'm pretty sure everybody knows, called the kubelet that interacts with, and then the kubelet is the one that is responsible to now create the sandbox and get all the containers running on that specific node. There's a bunch of interfaces that the kubelet uses in order to set up a sandbox, a controlled environment to run the image in, to run the container in. Runtime interfaces, network interfaces, storage interfaces, all of these get set up by the kubelet, and then it's going to create the containers inside that, okay? So we have the sandbox ready, and we start to create the containers, and we get the containers in them, and ultimately, after all of the containers in the pod are there, the kubelet is going to ping it on the next slide. And the kubelet checks that the pods and the containers are all ready, and then it's going to go and update etcd, and you'll keep on seeing more and more updates that go into etcd. So basically, it's a very complex, multi-step process. Starts on the control plane, goes into the data plane, a lot of moving machinery, a lot of components. The real question is, how long does it take? I mean, we want it to take as little as possible so that the pod will be ready to serve traffic as quickly as possible. The short answer is it really depends, right? I mean, there is no one answer because it depends on the load on the cluster, the load on your nodes, how quickly the scheduler can find an available node, whether etcd and the API masters are responsive or not. A lot of factors really coming in and affecting the startup time from when you actually submit your request to create the pod until it is there and running. In order to simplify that, Kubernetes defines an official service level objective, which is 5 seconds for the P99 under certain conditions. Again, they're trying to limit the amount of work or the variance that goes into how long does it take. For example, within this time, the kubelet needs to download images from a remote registry, right? So if it's a large image or the connectivity is constrained or there's a bandwidth issue connecting to the registry, it's going to take much longer. So in order to actually validate this SLO, they define it with locally cached images, right? I mean, they're going to try and limit the variance and get a result. So official SLO, 5 seconds for the P99. In other words, 99% of the pod creations are going to complete in under 5 seconds. This matches up pretty well with experiments that we did. What we saw was that the median was about 2.5 seconds on our clusters, and these were clusters that weren't doing really a lot of work. And the P99 goes up, by half a second or so. You might get different numbers on your clusters depending on the whole bunch of other stuff. So this has been like an introduction to what we want to talk about, and just to give you a baseline of where we are. And now, what happens when we actually take a look at adding Istio into the picture? How does that affect the startup time? And then we'll talk about how to shorten it.
Yeah, so let's see what happened when Istio is coming into the picture. So does anyone know what is Istio here? OK, I think I will skip the intro about Istio, so we'll have time to talk about the real stuff here. So just short, information about Istio. So as you know, Istio is being split to the control plane and data plane. The data plane is composed of a set of intelligent proxies that are being deployed as a sidecars. And those sidecars are controlling the communication between the microservices. The control plane consists of few components, which are and we will see later how it influences the startup time. The pilot that is responsible for the configuration of the sidecars, the mixer that is responsible for the policy and the telemetry, and the Citadel that is responsible for the strong authentication and authorization and the identity management of the service mesh. So let's see how Istio is coming into the picture. This is let's go back to the diagram that we saw before. So what Istio is adding? Istio adding, first of all, the sidecar injection webhook, which is responsible for adding and injecting the Istio-specific machinery into the pod definition. It adds, we will see later that it is adding the Istio proxy sidecar as one of the pod container. The second one is the Citadel. The Citadel control plane component is used to create the TLS certification for encryption, the inter-pod communication. This is a Istio init. This is an init container that is being added as part of the pod. It is coming before all the containers are coming. And it is responsible for to configure the pod's network to intercept the network, so the network traffic to go through the Envoy proxy. It is doing it by configuring the IP table inside the pod network. And Istio proxy. This is a container that is being added to the pod and is running actually the Envoy, the sidecar proxy in the pod. This Istio proxy is getting all the configuration from the pilot. So it's communicating with the pilot using XDS interface. And whenever it's getting all the configuration, it's using the readiness probe. It's informing the kubelet that the pod is ready, and it can start getting requests. So how actually all this together coming into time, and how much time it happened? So as you can see from our test, overall time is around 8.5 seconds, which is about 5 seconds more than what we've seen before without Istio. And what we see inside this 8.5 seconds, we have the Istio init time, which has to, as you can see here, has to complete before any other containers are starting. And after this time, we have the Istio proxy and the user container, which can be any user container that is running in the system.
Yeah, so just to explain a little bit about the tooling involved and what you're seeing in front of you. So we have a watcher that's running inside the cluster, looking at the pods that are being created and looking at the containers. And it actually goes ahead and creates distributed tracing spans. So things like Jaeger, if you know it, or Zipkin, we actually, based on those events, those status changes that we see, we create spans, and then we can visualize that in a very easy way. You'll see that you have, for each one of the containers, one or more spans. It's basically from the time that they were first created, the container was first created, first appeared, until it's transitioned in its state to being either complete, if it's an init container that needed to do some setup and then over, or it's switching into ready, running, or whatever, okay? What we do is, when we see it, we start the span. Whenever the container changes status from starting, downloading image, whatever, whenever it changes, we start and close the spans, and therefore we can actually see where is the time being spent inside the different containers. There is a shaded area to the left, which is some overhead that we have not been able to pinpoint. It happens inside the kubelet itself. We suspect that it's setting up all of the needed interfaces, namespace, et cetera, that you need in order to run the containers. The reason that we attribute it to the overhead of the kubelet and Kubernetes is when, you will see in a second, we remove the init containers, suddenly all of a sudden the other containers are going to be extended by the 2 seconds that are currently attributed to init containers. So there's like a 2-second overhead that we can't really do anything about it. We don't know what component inside Kubit is actually responsible for that, but it's not something that has to do with Istio or your own workloads, okay? Okay, so we just gave you Istio, which gives you benefit, or service mesh that gave you benefits, but we also gave you an extra 5 seconds, which I'm sure everybody just wants to get rid of, right? It's not a good thing to have. So can we improve? I think the short answer is yes, we can. And there are several techniques that you can do, and you can combine them to get most of the added time back. What can you do? The first option is to run the Istio CNI, and we'll go into detail about each one of those, okay? So Istio CNI is a different way to do the redirection, not using the Istio init component you saw a second ago, but instead of it using an Istio-provided CNI, a Kubernetes network interface, container network interface implementation, which doesn't alter whatever CNI you already have. It runs in addition to it. So if you're running Calico, Flannel, Cilium, whatever, it runs in addition. The only purpose of our CNI is to reprogram Istio. That gives you back 3 seconds. Nice improvement. Next, we'll take a look at playing around with the readiness probe. So as we said, the Kubit is going to test whether pods are ready to serve traffic, and it checks it on a schedule. If you shorten that schedule, you're not increasing the load by much, but you are saving time because they become ready sooner. We can talk about static proxy configurations. As you remember, as soon as Envoy starts up, it's going to call into the control plane and get its configuration. That configuration is dynamic. And if your use case warrants a static configuration, or it makes sense to have a static configuration in your case, then you can program it. And there are ways to override the dynamic nature of the configuration. Just have a static configuration. We'll show how to do that as well. Gives you back up to 2 seconds. And if you're really, down to the last millisecond and you absolutely need to have that, instead of having dynamic injections through the admission webhook, you can do that statically in your CI/CD by running Istio control inject and getting all of the setup done ahead of time. So Istio CNI, as we said, it's not a real CNI. It's not a CNI that is responsible for the networking in the cluster. It's only a CNI that is responsible for running the same IP tables, magic setup that's needed to redirect traffic from the workload into the Istio proxy inside the pod. There are benefits to it. We just talked about getting those 2-3 seconds back. That's one benefit. The other benefit is because all of the setup work, all of the networking privileged operations happens ahead of time outside of your pod, the pod doesn't need special privileges. It doesn't need to run with capabilities that are typically reserved for administrations of network functionality. This all happens under the CNI as part of the kubelet. So no need to leak extra privileges into your pod, another plus. The downside is that because the CNI programs all of the redirection to Envoy before Envoy actually starts, if you have any init containers that need to run and they need to have access to the network, basically that traffic could get black-holed because it will be redirected to Envoy and there's nothing there. Okay, so that's the downside. There are ways to mitigate that downside. If you have init containers that don't need any kind of network access, obviously it's not a problem. If you have init containers that need ports or IP addresses which are not shared or do not overlap with what is being used by your actual workload, you can tell Istio as part of the configuration to skip those. Basically say, don't trap those traffic flows, and therefore they will go to where they should be going. So if we apply Istio init, you'll see that we saved all the way. And you will see here those 2 seconds that we told you about before now are attributed to the workload and the Istio proxy. So the workload container, which is a very simple no-op container in our test because we didn't want to get noise instability into our system, it was extended from about 1.9 to 3.7. Similarly, the Istio proxy startup time expanded as well. So that was the Istio CNI. It is currently in development. It's available. You can try it. It's not a stable API yet. So if it's a production workload, we recommend playing with it, but holding off on actual usage for a little while. Next, as we said, there is a readiness. Basically, kubelet is going to probe the workload and the Istio proxy that was added to see, are you ready to accept traffic? And there is an initial delay, and there's also a period of how quickly it's going to test it. Right now, it's a 2-second delay, and you can configure it to lower. What we see in practice is usually the first probe, the one that happens after the grace period, does not succeed, but the next one, which happens after 3 seconds, succeeds. So if you change the period, which is a very harmless change in our view because you're only adding like one ping every now and then to test. Instead of doing this on a 2-second schedule, you're adding one network call on a 1-second schedule. So the load is not going to be significant, but there is a 50% chance that you're going to be ready on the second probe after 2 seconds and not on the first probe after 3 seconds. So on average, you're saving here about half a second. Configuration. The same configuration that we talk about here is going to be applicable to all of the other methods that we talk about. You can either change this when you install through Helm, and you can override the values, as you can see on the slide. You can also add the sidecar injection template to set the readiness probe to 1 second, and it's also up there. And in the case of the readiness probe, there's also an Istio annotation, which means that you can apply it on a pod-by-pod basis. You don't need to do it for all of your pods. You can actually get it done on a specific pod. The first two methods are going to do it globally, right? So if you do it on Helm, from the installation onwards, it's all going to change. If you do it from the sidecar container template injection, every new container that's going to get deployed will get the new readiness value. So from this point on, and if you do it on a one-by-one cases, then you have it that way. Next option that we played around with was to, instead of waiting for the Istio proxy readiness, there's another component that sits next to the proxy and basically makes the decision whether or not it's ready or not. The Istio proxy, the pilot agent, is going to see if the configuration was already downloaded, did Envoy reconfigure itself, can we start serving traffic. Instead of doing that, you can redirect the readiness probe at Envoy directly and basically say to Envoy, are you ready? Instead of asking Istio, is Envoy ready? This can save you a little bit more, and it is worthwhile in some cases. The problem with this method is that if Envoy is ready because it had its startup config parsed and the configuration is correct, but it didn't get all the cluster information yet, that means that any kind of connectivity into it might be a problem, or any kind of connectivity out of the workload is going to be a problem. So if your code or your callers are going to be retrying that connection, they're going to go once, it fails, go twice, 3 times. So if you have resiliency and retries built into the rest of the system, that is a change that you could make, and it will be ready faster, and you can start redirecting traffic faster. But it really depends on the way that you program the rest of the mesh. So not something that we necessarily recommend. This too can be changed through either the Helm config or through the sidecar injection. Okay? So same methods as before. By the way, all of the slides are online on Sched. You don't need to remember any of these. If you need to refer to it later on, it's there. See if I wanted to say anything else on this.
This is disabled.
Yeah, so the last thing you can do is you can decide to disable the readiness probe completely. And this is certainly not something that we would recommend doing, but what we did do is we wanted to see if there was, what if Envoy or the Istio proxy was ready immediately? How much could we save, right? So it's only to motivate the fact that we wanted to try a static configuration. Right now it takes time because Envoy needs to connect into the control plane, download stuff, process stuff, combine it, manipulate it, load it, reconfigure itself. What if we gave Envoy all the configuration that it needed so it was immediately ready, right? So the amount that you can save, we simulated that by actually disabling the readiness, which means it's ready when it's started, right? So there's no need to ping it and see if it's ready or not. So another 1 second that you can actually cut down. What do we mean by the static configuration? Envoy has a bunch of XDS interfaces, cluster discovery, endpoint discovery, secret discovery, listen. So a whole bunch of dynamic stuff that it can get. It's a programmable proxy. And you don't necessarily need all of that dynamicity in a real system. For example, if you're using something like Knative, everything goes from the services through the ingress gateway. So in fact, you actually know everything that's needed for Envoy and all of the envoys in a Knative installation when you're already deploying it. Yeah. So if your topology is known in advance, if you know your dependencies well in advance, as we said, Knative is being one example. It's not easy to configure. It is something that you can actually configure today if you wanted to, but it's not friendly. It is something that we need to take a look at as the Istio team and figure out if we want to expose that, at least for the use cases where it makes sense. Because as we said, it can cut down another 2 seconds of startup time. And you can actually have a combination of a static and dynamic config. You could have, let's say, all of the clusters are known in advance. So I'm going to have a static CDS, but endpoints I want to populate at runtime, so I'll have a dynamic EDS. And any kind of combinations, all of these require more programming, and we have some ideas on what we can do. For example, start with a static config and then overlay it with the dynamic properties as they become known asynchronously in the background, as opposed to having Envoy actually block and wait until it gets the full config. 2 methods for doing this. If you wanted to override the default configuration or have additional properties that go into the default startup config, you basically create an Envoy configuration file, which means you need to understand Envoy's configuration in detail. It can be complicated, but if you are adventurous and you can grok the entire configuration, create it, create a file, store that file in the config map, and then annotate the pods to use the startup config that you created instead of the default startup config. Second method is to completely replace the startup configuration. So previous one gave you the ability to merge additional properties or override properties if they were defined in your configuration as well. If you want to do this instead by completely overwriting, then again, you create a full configuration file, you store it in config map, but instead of annotating the pod, now you're going to change the config in a way that maps that config map into each one of the pods as a volume and tells Envoy through a command line interface to use the new startup configuration. Okay? Last, and if you made it so far, we can give you another 15 to 20 milliseconds by doing manual Istio inject. Not much to say about it, but it certainly is something that if you care about performance that much and you want to do it in your CI/CD, that would be a good place to do it. And that way you don't need the admission webhook, the mutating webhook inside. So in summary, we saw that we added 5 seconds or so to the startup time. And if you use the Istio CNI, 3 seconds, the majority of that is already coming back at you. Another half a second by shortening the probe, the readiness probe. If you're OK with actually retrying communications, you can cut down another half a second by changing it from the pilot agent startup probe to the readiness probe of Envoy itself. Static configuration, again, helpful, very helpful, but it is a complicated thing. So proceed with caution. And the last one, I think, is mostly for fun. That's all we had for today. Be happy to take questions. Right? Yeah.
Thank you.
Thank you for the presentation and outlining where the time is spent. I was just curious, when you made this test, is there a way I can see how you arrived at these numbers?
Yes. Are we planning to open source that part?
Not sure about it.
We can make,
we can
make it available. I'm not sure we will invest time in open sourcing the entire framework. We may want to do that as part.
Share it,
but we can certainly share it.
Because I keep getting these questions about how performant is Istio. You know, it is complicated. There are easier ways. That seems to be the big question. And I know I tried to do some performance testing. Of course, I tried at 1.1, 1.2 levels. I don't know which version this is.
1.3.
This is,
1.3, yeah.
Yeah.
So, and again, one of the component of Istio is a mixer, which goes away in 1.4.
Yeah.
So I guess, I mean, if I find this kind of information, not just as a session, but also as a blog or whatever.
Okay. We are planning, first of all, to have
specifically
a blog
with more specifics.
So I think performance is a big question, and you're right. There's startup performance, which we talked about here, and the focus of this talk. There's runtime performance, latencies, bandwidth, et cetera, which obviously we did not touch on.
Yes.
I know there is a performance work group within Istio, so we are very much minded towards that as well. This work has been presented to the performance work group, and
sure, I'll probably get added to the channel.
Yeah.
Right now, I'm still getting some things ready. Yeah, this is awesome. I really liked it, but specs, I mean, devil is in the details. I mean, it is nice that you also spelled out what could help with each of the microsecond, cut down and where it could help. I like that as well. Yeah, awesome. Thank you.
Thank you, and if you come by later, just give us your card. We'll give you a Mal card, and we can see how to make that information shared to anyone else, of course.
Thank you for great talk. Do you think you mentioned that the time to take for pulling images is out of scope for the SLA, but do you think how critical the time to take for pulling image is, and do you have any idea to mitigate it?
Do you want to take that? Do you want me to take it? So the problem with downloading and counting that time is really, it is out of our control, right? I mean, if you have a 1 gig, 2 gig image, obviously it's going to take much longer than a 20 meg image. And when we do a performance comparison or we try to optimize it, if the numbers are going to be skewed towards the large download time, everything else would be noise, right? So that's why we try to eliminate that from the picture, and it's also what Kubernetes tries to do with the SLO. It's saying all images are cached, because if you have too much variance, it's outside of our control. Nothing we can do about your image size, your transfer rates, whatever. I know that there are some projects not related to Istio in any way. I think it's a generic Kubernetes question, that try to optimize the download by doing some kind of a peer-to-peer transfer. So instead of going to the registry, taking it from nearby host if they have it cached. I don't remember the names of the projects, but there are some out there. I think startup time makes sense to worry about, and it's important, especially if there's somebody waiting for that response time. So it's important if you can cut down on your image transfer. By all means, try and do that. It depends on your runtime environment. Go statically compiled executables, much smaller than doing from Ubuntu and then getting the entire JVM in there and whatever, right? So if you can do anything about it, it helps. More questions? Yes.
Thank After looking at all this profiling data, was there anything that you decided to take out of your service mesh because it was just kind of overkill for it? It wasn't worth the performance penalty it was imposing?
So as I said, we are looking at the startup performance. It's a limited view. I think that it's not that we decided that it's a bad idea to have a service mesh. It's obviously a trade-off. You're getting benefits out of it, and if you need it, then you want to use it. And I think our focus is actually trying to optimize up to the point that it's not painful anymore.
There is more work that is being done as part of doing more performance profiling of the entire Istio. And there we are trying to find where exactly are the pain points and how can we influence there and decrease the time.
And plus, maybe as a side note, we are part of research, so we get to play with stuff. We're not really responsible for deciding whether or not to take the service mesh out or not. Yeah. We did this out of trying to optimize Istio and because we felt that this was an interesting problem for us to look at.
So that's all we have time for right now. Thank you everyone for coming. Please fill out your feedback forms. If you have any other questions, our speakers will hang around for a few minutes, I think. So thank you all again.
Thanks.